This is the second part of the tutorial and illustrates how to generate a structured mesh in IsimCFD, define periodic boundaries, improve the quality of the blocking, and define the boundary conditions for the simulation. We start the blocking by creating the main block which surrounds the body we just created, named as fluid. We need to split the block into multiple parts in order to follow the geometry as much as possible. Next, we need to associate the edges of the block to the curves of the geometry. Make sure you enable the project vertices option for moving the edges to the new position. As you can see, some of the vertices here do not exactly follow the geometry, therefore we can move them using the mouse in the move vertex option. They only move along the edge, the curve direction, as they are already associated to it. At this point, it's important to clarify that blocks are used for defining the mesh, and they are based on the geometry. However, after creating the mesh, the geometry doesn't exist. So instead of having points, we have vertices. Instead of having curves, we have edges, and instead of surfaces, we have faces. Now, if we turn off curves under the model tree, we can see that some of the edges are green, and that simply means that they are associated somewhere. We need one more split here, and this is because of the blade curvature. We perform the association in the same way as before. Even if the edges here do not exactly follow the curve, this is not a problem. As far as they are associated, the mesh will follow the geometry. And if we want the coordinates of our top vertices to match the coordinates of the bottom vertices, we need to use the align vertices option here. The next split will be in the middle section of the span for dividing the edge into parts with different sizing. And one more split is needed here in the middle section of the pitch for the same reason. So after finishing with the splits, we have to define the sizing of the edges. We need to click on pre-mesh parameters and then edge parameters. Make sure that after selecting the edge, you enable copy parameters. That copies the sizing to all parallel edges. First, we define the number of nodes. So you can see we have 20 nodes in this direction, and the mesh law, which is exponential 1. Exponential 1 means that the spacing of the nodes will increase in the same direction as the arrow. The spacing of the first cell will be 0.4, and then it will grow with a growth ratio of 0.1 to 1.2. Make sure you have a growth ratio of 1.2 or lower. Now we chose exponential 2 because this edge has the opposite direction. The arrow in this edge has the opposite direction. Again, we have smaller elements near the airfoil surface in order to capture the viscous effects when the fluid comes in contact with a wall. The number of nodes here will be 34. The spacing of the smallest cell will be 1. We have small elements near the blade leading edge, and then it starts increasing. We are going to choose exponential 2 for these edges, and that's simply because the direction of the arrow is opposite to the direction we want our spacing to increase. The mesh is finer near the trailing edge. This is because small scale effects are expected in this region of flow. After finishing with sizing, we can compute the surface mesh. The solid option gives us better visibility of the mesh, therefore we can activate it here. We can also check the number of nodes of the volume mesh we just created. The quality of the mesh is important for the CFD solver, and one of the quality criteria is the angle. All of our elements need to have an angle higher than 18 degrees. If we click on the low quality elements here, we can see them on the screen, and they are located in the high curvature regions. If we take a closer look, we can see that the problem is the small angle between the edge and the blade surface on the leading edge. Therefore, we can move the vertex here and increase the angle. The vertex will only move in the x and y direction. The z direction will stay fixed. Now compute pre-mass to check if the quality is improved. It's slightly improved, however some of the elements still have a low angle. We need to increase it even more. Compute pre-mass again. Now the leading edge region is fixed, and now we can focus on the trailing edge, which has the same problem as before. The angle between the blade and the edge is small, and we need to move the vertex to make it larger. We compute the pre-mass again, and we can see that the low quality elements have moved to the opposite side now. This is because by increasing the angle on the lower side, we decreased the angle on the opposite side. We cannot move the vertices anymore, therefore we are going to edit the edges. By default, edges are straight lines, but we can modify them. If you do something wrong, then click undo. We are now modifying one of the edges and then link the other two to the reference edge. The quality is even worse. We click undo to return them to their original position and shape. The reference edge and the other two that we need to link them. The quality is lower than before, and that shows that we need to bend the edges to the opposite direction. Therefore, we click unlink ends and we select all three edges. The edges are straight lines again. Now we need to bend them to the other direction. We modified one of them and then link the other two to the first one. After bending these edges, a small angle is created between the horizontal and the vertical edges. But we can't bend this horizontal edge as well to fix the problem. We use the same method as before. We link the other two edges with reference to the first one, and then compute pre-mess. All of our elements have an angle higher than 18 degrees now, so it's all fixed. We can also check other quality criteria, for example the determinant 3 times 3 times 3. All of our values here need to be higher than 0.3, and our values are well above this number. We can now define periodicity. We need to click on Mesh, Global Mesh Setup, and then Set up Periodicity. Enable Define Periodicity and choose Translational Periodic. The distance of the periodic phases is 60 on the y-axis. And now we need to specify the periodic vertices in pairs of 2. This vertex will be periodic to this vertex, which means that the flow on the first one will be the same as the flow on the second one. And then we repeat the process for the rest of the periodic vertices, both upstream and downstream. After finishing with defining periodicity, we can check the number of elements in our mesh. Right click on pre-mesh and then select pre-mesh info. We can also convert to unstructured mesh. This is necessary as the CFD solver does not recognize structured mesh, so we have to convert to unstructured. If we click on edit mesh, we can check for any errors. Here we need to specify the periodic phases. Then select the solver, apply, and then set the boundary conditions. You can set the boundary conditions either here or in Fluent. As you can see, some of the surfaces are one-sided, some other two-sided, and some other mixed unknown. It doesn't really matter what your surface type is. You can specify conditions, boundary conditions in any type of surface. Now the last step is to write the files, and that includes both the mass and the boundary conditions.